Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the system of particles and rotation motion. Let us begin with the concepts of body. The body is here, we are going to consider as rigid body. Rigid body means here ideally defined as when the load is applied on the body, the distance between the two particles remains unchanged. That means it doesn't change. Then that body is known as rigid body. So in real condition, in practically, there is no rigid body. So when the load is applied, all bodies, real bodies are all ideal conditions. There's all real bodies, all flexible bodies, not considered. But here we are considering the bodies with the negligible deformation. That's why we are going to consider them as rigid bodies. Now the types of motion under rigid body. The rigid body can have two types of motions. One is pure translation, another one is pure rotation. So here, what is the pure translation? Motion of a block. Suppose if you can see the motion of a block under here, that is motion of the block on an inclined plane. So there are 2 points. There are two particles are there. There are 2 points P1 and P2. It doesn't change. In pure translation, all particles of the body have the same velocity at any instant of time. That is P1 and P2. So here, that's what the main thing here. The particles P1 and P2 having the same motion here, having the same velocity at any instant of time. That motion is known as the pure translation. Coming to example 2, the motion of a vase on a parabolic path, the projectiles. So the motion of a vase, the vase, if we consider it, here it is on parabolic path. Okay, that parabolic path of the projectile of the vase, if we consider on that, the velocity of the particle is same. That's why here, but the body is restricted to move only with the translation. Now here all particles of the body have the same velocity at any instant of time. So by considering this principle, we can decide the body, whether the body is in translation or in rotation. How can we know if the body is a translation or rotation? Based on this principle only, we can say that, or we can come to conclusion that the body is under translatory motion. How can we know that? Again, here the vase is moving here in this direction. Okay, but the vase is not rotating and moving. Okay, that comes under combined translation and rotation. So if the vase is rotating about its own axis, then the body is under a rotary motion. Okay. Now here the direction of the velocities of various particles will be parallel to each other or tangential to the trajectory at any instant. So what is that meaning here? The meaning of this sentence is that the direction of the velocities, if we consider the direction of the velocities of the various particles or different particles, if we consider, will be parallel or tangential to the trajectory at any instant. So based on that, the body is under pure translation. Now the combined translation plus rotation, the combined translation and rotation. What is the combined translation and rotation? We can consider the rolling of a cylinder on inclined plane. So how can we know that rolling of the cylinder on inclined plane? Suppose if we consider the inclined plane having an angle theta, and the cylinder, if we consider it, the cylinder, it rotates and comes down and also it moves down. So it is a combined translation and rotary motion. Okay. Now here we consider a wooden or metallic cylinder rolling down the inclined plane, undergoes both translation and rotary motion. Now there are various points, various parts you consider P1, P2, P3 and P4. Yeah, the way we consider this direction of the velocities, we can see it, how it will be rotation and all. So the velocities of P1, P2, P3 and P4, the same instant at a different depending on the location on the body, and the velocity P4 is 0 when it comes down, when it touches the ground without any slipping contact surface. Now the translation as well as the rotation of a vase as a projectile. So if we consider the vase consideration, both rotation and translation, the vase is moving. How it will moving, you see, it is moving translation at the same time rotary motion. That's why this vase is having the combined rotary and translatory motion. Okay, so the body is moving with the translation as well as rotation. Now the particles of the body have not the same velocity. It is having a different velocities at any given instant of time. That's why the body is under translation as well as rotation. That's what we consider the ways. So the direction of the one more thing is that direction of the velocities of the various particles will be different with respect to trajectory at any given instant. It is not same for this case. Now coming to the second motion, that is a rotation. What is the meaning of rotation? In a rotation, the body rotates about a fixed axis, but every particle of the body moves in a circle which lies in a plane perpendicular to the axis and has its center on the axis. The point is that it rotates. The plane of rotation is perpendicular to the axis. That is the meaning. Suppose if a vase is having, it is rotating in a circular direction. The direction of the rotation, rotary plane, that is perpendicular to the where? Perpendicular to the body. That's what the meaning is here. Okay, if you consider the fan rotates, ceiling fan rotates the axis of the ceiling fan, and it is rotation, the rotary motion is in this direction. And if you consider a pot is made on a circular wheel, so how the pot is making circular wheel and is the axis, and what the pot maker makes to rotate, when the wheel rotates in this direction, the wheel rotates at the same time the rotation, the axis of rotation, and it will rotate along its the plane here. Okay, it will rotate in this direction completely. Now another some of the examples, if we consider the fan about rotating about its axis, the table fan rotating about its axis, the axis is perpendicular to the screen. And if you consider another, okay, another the thing which is rotating about its axis, a spin rotating about its axis vertically. This is the vertical axis. And if you consider the pot, as I mentioned, the particle is rotating about its axis. Okay, about its vertical axis. These are the examples. Now here, if we consider the rigid body is rotating about y-axis or x-axis or z-axis, so considering here a rigid body is rotating about y-axis, now with the x-axis, axis x and axis y, it is rotating about y-axis. So and it is x, y, z. There are three axes we consider, but in this case the body is rotating about y-axis. And if we consider another body, okay, another body is rotating here. It is rotating about, but what is the plane of? It is rotating about y-axis. What is the plane? The plane is normal to the y-axis. What is the plane? X and Z. That's why the plane of rotation, the plane of circular, the particles describe circular motion, but the plane lying on which plane? That is XZ plane, that is perpendicular to axis Y. And similarly, another, the body, it is rotating about Z-axis. Yes, these are the Z-axis. It is rotating about Z-axis, but it is lying that plane. The plane of rotation is on XY plane. Okay, this is what the particle rotates about Z-axis and it lies on XY plane, that is perpendicular to Z-axis. If it is rotating y-axis, what is perpendicular to y-axis is XZ plane. So the XZ plane is perpendicular to y-axis here, and the plane is rotating here about Z-axis, and it's the perpendicular is XY. Okay. Now coming to the one of the motion, that is called precision. What is the meaning of precision? The precision means by considering rigid body, we are considering as a rigid body. Here, in the precision of a rigid body about a fixed point, the axis of rotation itself rotates about another axis. Rotates about another axis passing through that fixed point. What is that meaning? Let us understand through the diagram. So now here is the axis of rotation itself, and about another axis passing through that fixed point. In a precision of a rigid body about a fixed point, this is the fixed point. In the precision of a rigid body about a fixed point, the axis of rotation itself about another axis passing through that fixed point. This is a fixed point. Now how it is rotating, you can understand. So the rotation is that is the rotation. That is known as the precision motion. Okay, like that the precision motion takes place. Next, furthermore, we are going to explain about the precision. In precision motion, in the case of precision, the axis of rotation is not fixed, but the point of contact point is remains the same. Okay, and at any instant, the axis of rotation passes through which point? The point of contact. That's what happened here. These remains same, the axis of rotation, but the fixed point remains same, and the axis always remains in contact with the fixed point. That's what the point of contact. And one more thing is that in the case of a table, oscillating table or fan or pedestal fan, the blades are rotating about an horizontal axis. That is, here it is z axis. When it is rotating about z axis, the plane is xy plane. Okay, but the arm carrying the blades rotates about a vertical axis. Next one, the meeting point, both horizontal and vertical axis is okay at O, that is remains fixed. So the point contact is remains the same, whatever the rotation may be. So if it is if the rotation is about z axis, the plane is xy. If the rotation is about y axis, the plane is xz. But the point of contact is remains same. So in precision axis, so thus in precision, the axis that is on one line is not fixed, but one point is remains fixed. That's what. Okay. The next important observations in precision motion, what we observed in the case of precision. In the case of precisions, the observed motions are the observed points, important observations are in the case of complete, what you have studied, view translation, motion and rotation motion, and also the motion in precision. What are the observations were made in comparing by these three motions? So the motion of a rigid body, which is not pivoted or fixed in ways in either pure translation or combination of both the translation and rotation. So if we consider, very important is that if you consider a slider crank mechanism, that is the crank and a slider, is the fixed point O, A, and it is B. It is a link 1, link 2, link 3, and link 4. Let's say a fixed link 1. So link 2 is known as a crank. Link 1 is known as a fixed link. Link 2 is a crank. Link 1 is a fixed link. And what about link 3? The link 3 is a connecting rod. And link 4 is a slider. Now, what are the motions of link 1, link 2, link 3, and link 4? By observing this motion, here the crank is always in rotary motion. The crank link 2 is rotary. This mechanism converts the rotary motion into reciprocatory motion. Now, the link 1 is fixed. The motion of the link 1 is 0. It is fixed link. Whereas the motion of the link 2 is a rotary motion. And motion of the link 4 is a translatory motion. Link 4 is under translation and link 2 is under rotation. What about link 3? This link 3, 1 and A and B, if we consider, this A is under rotation, B is under translation. That's why the link 3 is having the combination of rotation and translation. Sum of translation and rotation. These two motions will be the link 3. As we have seen, why at any instant of time, the points on link 2 is under pure translation. The particles are the points on 2, if we consider, it is under rotation. At any instant of time, the points on the link 4 is under translation, the velocity. Whereas at any instant of time, the velocity is, the direction of the velocity on link 3 is the combination of translation and rotation. It is the best example of understanding the translation, rotation, and combined translation and rotation motions. Okay, now there is one here, the observation we made it that The motion of rigid body which is not pivoted or fixed in some way or other is under pure translation. If it is not fixed, then it is under either pure translation or pure rotation or combined both. That's what the meaning of first point is. The next observation is that the motion of a rigid body which is pivoted is fixed somewhere is rotation, which is pivoted or fixed in some way is under rotation. Next is that coming to the rigid body, the particles under motion, coming to here, the center of mass. So the center of mass of two particles along the x-axis system. So we are consider a two particle system. We are considering two particle system along the x-axis having with masses m1 and m2. And at a distances of those two masses are x1 and x2 from the origin O. That's what here. The m1 is one of the point here, and that is at a distance of x1, and m2 at a distance of x2. Okay. Now the point of center of mass is between these two. How it comes with respect to the OY. Okay, but these two masses are on along the x-axis on OX axis. Now here the center of mass distance from OY is xcm distance. So how to find out the xcm distance? The xcm is that m1 x1 plus m2 x2 by m1 plus m2. This indicates the distance of center of mass from OY. That is the reference axis. So here if the two masses are same, m1 and m2 both are equal, m1 and m2 equal to m, then what will happen? The center of mass, the distance of center of mass along the x-axis, that is mx1 plus mx2 by 2m. So if we make it common, m into x1 plus x2 by 2m, get cancelled, then x1 plus x2 by 2, that is the center of mass. That's what x1 plus x2 by 2. Now here, but the meaning is that the two particles of equal masses, if the two particles are having equal masses, the center of mass lies exactly where it is midway between them, the average of between these two, that is the midpoint of this x1 and x2. Okay, x1, x2, that is x2 minus x1. Okay, x1 plus x2, but that is the midpoint, mid of this distance between m1 and m2. Now coming here, by going to consider, if we consider three particle system, suppose if we consider a three particle system on that is m1, m2 and m3. These are at a distance of x1, x2 and x3. Where is the location of center of mass? This is OY and it is x. Where is the location of center of mass? The center of mass location can be calculated by, that is m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3. That is the center of mass, a distance from center of mass. So it can become anywhere. We may not get it here. The center of mass location, this is xcm, that is the cm, center of mass. The center of mass location is xcm. Okay. Now suppose if the masses are having equal masses, this m1 equal to m2 equal to m3, that equal to m, then what will happen? Can we tell? But the center of mass xcm equal to x1 plus x2 plus x3 by 3. Okay, if m1 equal masses, so the average, that is the x1 plus x2 plus x3 by 3. That is what if you can understand like that. Suppose if n particles are there along the x-axis, for n particle system we are going to consider along the x-axis which are having the masses are m1, m2, m3 and so on mn at the distances of x1, x2, x3 and so on xn from the origin O. Then the center of mass of the system, how to calculate? Directly also you can tell what is the center of mass. xcm equal to m1 x1 plus m2 x2 plus and so on mn xn by m1 plus m2 plus m3 and so on mn. Okay, if equal masses, then this is also can be written as sigma mi and xi, where I equal to 1 to n upon sigma mi, where I equal to 1 to n. So this is also center of mass for n particle system. So let us see here. This is the equation. Yes, xcm center of mass equal to, and it is sigma I equal to 1 to n, that is mi xi by sigma I equal to 1 to n. Okay, this is the parametric or generic formula for n particle system, the center of mass for n particle system. Next, as we studied that, consider three particle system. Now it is three particles. The three particle system are so far in unidirectional along OX axis. Now it is in different coordinate system on XY plane. Now these three particles system are on XY plane, which are having at the coordinates of three particles are x1, y1. That particle 1 is at a coordinate of x1, y1. And particle of second coordinate, the particle of second particle is at a coordinate of x2, y2, and the third particle is at the coordinate of x3, y3, and having a masses of m1, m2, and m3. Now for that case, m1 is at x1, x2, m2, x2, y2, and m3, x3, y3. For such system, how to find out the center of mass? Okay, the center of mass will be considered. Then there are two things. It is on xy plane. There are two things you have to find out. One is, again, the center of mass is also having a coordinate. That coordinate system is xcm and ycm. How to find out such things for xcm and ycm? That is the here for xcm m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3, and ycm is m1 y1 plus m2 y2 plus m3 y3 by m1 plus m2 plus m3. Now these masses are having equal masses. This m1, m2, m3, and these are equal masses. m1 equal to m2 equal to m3 equal to m. Then what about xcm and ycm? The xcm is x1 plus x2 plus x3 by 3. What about ycm? The ycm similarly y1 plus y2 plus y3 by 3. Okay, if m1 equal to m2 equal to m3, that equal to m. Okay, for equal masses. Now this is what then, as I mentioned here, x1 plus x2 plus x3 by 3 and y1 plus y2 plus y3 by 3. Please understand here the plane is xy plane. We are considering only single plane, that is a two-dimensional. Before these masses are on only OX. Now we can interpret more better and come to here, we can discuss further more. Suppose if the masses are along y-axis at a distances of m1 and m2 are at a distances of, I'm considering two particle system, at a distance of y1 and y2. If you want to find out the center of mass for this, what about that center of mass is comes under, that is ycm, center of mass in y direction. How it comes again? m1 y1 plus, what about ycm equal to m1 y1 plus m2 y2 by m1 plus m2. And if the masses are equal, then it happens, what will happen? y1 plus y2 by 2. If m1 equal to m2, then what will happen? ycm, the center of mass in vertical direction, that is along the y-axis, that is then it becomes y1 plus y2 by 2. Okay, thus we have to find out, we consider only in one direction, that is OX, on OX axis. Now I have shown you that on OY axis also. Now the combination these two, that is the two-dimensional, that is the plane consideration, that is XOY plane. Alright. Now let us come to here some of the things. Now n-particle system, for a plane n-particle system, how it becomes n-particle system? There are different planes here, m1, m2, m1 is at a coordinate of x1, y1, z1, and m2 x1 y1 z2 and x3 y3 z3 and so on. Okay, there are different and so on. Mn, xn, yn, zn coordinate system. For three-dimensional, it comes under the category of three-dimensional category. Then what are the things will come out? This is the coordinates are x1, that means xcm, ycm and zcm. So for that xcm, that is m1 plus m1 x1 plus m2 x2 plus and so on mn xn by m1 plus m2 plus and so on mn. That is xcm. What about ycm? The ycm is m1 y1 plus m2 y2 plus and so on mn yn by m1 plus m2 and so on mn. And zcm is this what? xyz. So these are the things can be written in the form of algebraic equation, some equation integral form. That is mi xi, where I equal to 1 to n upon sigma mi, where I equal to 1 to n. Similarly, ycm equal to sigma I equal to 1 to n mi yi by sigma mi I equal to 1 to n. Similarly, here zcm equal to sigma I equal to 1 to n mi zi by sigma I equal to 1 to n. Okay, sigma I equal to 1 to n mi. In that manner, we can also make in the form of integration. Okay, this is what here mentioned one by one. And here this mi zi by sigma equal to 1 to n. Okay, now what about this sigma mi? If you consider, understand, this is sigma mi I equal to 1 to n, it is nothing but a total mass. And it is also total mass, it is also total mass. The total mass is common here in the denominator. Okay, and whatever mi iy, this mass into the distance. Okay, it is also kind of the momentum. Okay, let us begin here. Now coming to the vector notation of center of mass. What is the vector notation? Now we are going to vector notation. Now these all these equations are we are going to mention the form of vector notations. Now that is ri equal to xi I times I plus yi times j plus zi times k. Okay, and here ri is the position vector, whereas the this xi is ith direction, that is the ith particle, and capital R is the position vector. Small r is the small ri is the position vector of the ith particle, and whatever capital R is the position vector of the total system, center of mass of the system. For that it is denoted for the capital letters. Now in the vector form, the center of mass is position vector, that is sigma I equal to 1 to n times mi ri by sigma I equal to 1 to n times mi. This sigma I equal to 1 to n mi means it is the total mass of the system. Now here coming to the center of mass of a rigid body. Okay, now this rigid body is having a rigid system is completely closed packed particles. So the equation is described here applicable to a rigid body. Now these are the things which we can discuss for Mn particle. For Mn particle, here it is sigma equal to the center of mass I equal to 1 to n times delta mi xi by sigma equal to 1 to n times delta mi. Similarly, y and also z direction. So here the body is the whole complete body is divided into small particles, n number of small elements. Each element is having a mass of delta m1 and delta m2 and so on. Okay, and here the ith element delta mi, for ith element delta mi is taken to be located locally, that is location point xi, yi, zi. So the coordinates of the center of mass are approximately this what are given by equations xcm, ycm and zcm. Now it is n is made bigger and each delta mi becomes what? If n is made number of elements, the number of elements are more, then del mi becomes smaller and smaller. Okay, then what will happen? The solution becomes exact solution, more accurate solutions. Okay, now for that, in order to reach in the case, we are going to use integrals. The del mi integral del becomes this integration, the sigma of del mi becomes integral dm. This integral dm is nothing but a total mass m. Now the term del mixi then becomes what? Integral x dm. Similarly, in y coordinate system, sigma of del mi yi that becomes integral y dm. Sigma del mi zi becomes integral z dm. Now we convert all those sigma terms in the case of integration form, then becomes this x dm by m, x cm equal to integral x dm by capital M. Similarly, y dm equal to y cm equal to 1 by m times integral y dm, and z cm equal to 1 by m times integral z dm. This is the more, because here the number of elements are bigger, the n is the number of elements are more and more, then the del m may become smaller. Further, the integral, we are using the integration to get the exact solution. Okay. Now, in the case of vector form, we want this vector form, that is 1 by m times position vector, the position for 8th element, that is r dm. Okay. Now, consider the center of mass of a thin rod. Here, this is the thin rod. This thin rod is having element is dm. At a distance of O, the distance of dm from O is, that is the x, and both we consider is the negative x and the positive x axis. Okay, and the radius, whose radius here, the radius of the thin rod is very smaller along its in relation to the length. Now the net contribution of this here, that is x dm itself is 0 for of such pair, the integral, and hence the integral of x dm itself 0. Why? Because the positive and negative is considered. Both will be balanced. It is in equilibrium. Both will be balanced. Then what will happen? The sum, net sum becomes 0. Okay. Now here the point where integral, the point where integral is 0, that is a completely balancing point. That means that point is the center of mass. That means it will be balanced equally. If you consider this, yes, it is like a thin rod. If you consider it, the finger is supported here, the finger supported, and it is completely balanced. The mass on left side and right side is completely balanced. That's why the center of mass is where it is located. This point it is located. Okay. Now the motion of the center of mass, let us discuss here. Here the position vector r vector is equal to sigma I equal to 1 to n mi ri by capital M, where sigma I equal to 1 to n mi ri equal to, that is nothing but m1 r1 plus m2 r2 plus and so on. This complete combination is make it as mr. This mr by m, differentiating the two equations, that is both sides with respect to time, m dr by dt equal to m1 dr1 by dt plus m2 dr2 by dt and so on, mn drn by dt. Now this dr by dt, what will happen? It is nothing but a position vector with respect to time. That means displacement with respect to time. That is nothing but ds by dt or dx by dt. That is nothing but velocity. That's why it is converted into m into v. Momentum equal to m1 v1 plus m2 v2 and so on, mn vn. Now this mv vector equal to m1 v1 plus m2 v2 plus and so on, mn vn. Then again, if you differentiate this two sides equation with respect to time, this velocity by time, then what will happen? Acceleration dv by dt. Then that is both of, then the total, that m into dv by dt, that is m into a. Mass times acceleration, m into a equal to m1 a1 plus m2 a2 plus and so on, mn an. So this is nothing but what? Newton's second law, F equal to ma. The force acting on the first particle is given by, that is F1 equal to m1 a1, F2 equal to m2 a2 and so on, and Fn equal to mn an. That F1 plus the sum of F1, F2, F3 and so on, Fn equal to total F, that the total force. Okay. This total force, okay, the total mass of the system of particle times the acceleration of its center of mass is a vector sum of all the forces acting on the system of particles. Okay, this is the Newton's second law of motion. How it is so magical? We started with center of mass. Why center of mass is connected to the motion of the particle? This is the manner. Now center of mass we consider, three-dimensional we consider, then with respect to time, okay, and then what will happen, convert into velocity vectors, and from that velocity into acceleration. Finally, we obtained as from center of mass, obtained from that the Newton's second law of motion, total force acting on that. Now here some of the things. When we talk of the force F1 on the first particle, here it is not a single force, but it is the sum of all the forces on the particles. Okay, likewise for second particle, third particle, and fourth particle, and so on up to n particles. So finally, the total force, that is m into a, equal to external force, that is F external force, the total force. Okay, this external force is the force acting on a sum of the particle total, acting on the particles of the system. Now, why it will happen here? Why we are considering here? In the case of vibrations, if we consider the simple pendulum concept, in the case of simple pendulum, okay, the tendency to move the simple pendulum here and here in this direction. Here the force F acting on the force, it is directly proportional to the displacement or displacement of the body, and it is in opposite direction of the motion. Okay, so external force, unless until some external force acts on the body will remains at rest or it continue in a state of motion. If the body is at rest, if you want to change the position of the body, we need external force. If the body is in motion, if you want to stop, that means change the position of the motion, means make the rest, we need external force. That is the Newton's second law of motion. Okay. So to determine the motion of the center of mass, here we need to we have to use this mass times acceleration, that is a force, external force. That's what here. Now, coming to your linear momentum of a system of particles. What is the linear momentum of a particle? The linear momentum of a particle is, as we defined here, linear moment, that is mass times velocity. That is what we calculated. That is P, capital P equal to P1 plus P2 plus P3 and so on Pn. That is the total momentum is the capital P. Now here, F equal to, if you make it Newton's second law, F equal to dp by dt. It is nothing but m into dv by dt. That is m into dv by dt, m into a. That is known as F. For n particles we want, then that is P equal to the sum of P1, P2, P3 and so on Pn. That is where is P1 equal to m1 v1, P2 equal to m2 v2 and P3 equal to m3 v3 and Pn equal to mn vn. Okay, and this total mv is nothing but m into v. P is the capital P is m into capital V. That is mv equal to m1 v1 plus m2 v2 plus m3 v3 and so on mn vn. This mv is the capital P, m1 v1 is the p1, m2 v2 is the p2 and so on pn. Okay, now that is differentiate this moment with dt, that is m into dv by dt, as we get it dp by dt equal to m into dv, that is m into a. This dp by dt is the force equal to m into a. Okay, that's what external force. Again we proved the external force. Now we want external forces on the particle, it is 0, that is a dp by dt equal to 0. Then what will happen? The p becomes 0, p becomes a constant. When the p becomes a constant or p equal to constant, okay, if the sum of external forces acting on the particle is 0, that means the moment the particles acting is equal to 0, that is p equal to constant. What is that meaning? This statement indicates that law of conservation of linear momentum of a system of particle. This is the statement. So we covered in this session what are the motion of your particles, the basics, and also we came from basics of the center of mass, how the pure translation, pure rotation, combined translation and rotation, and also center of mass. From the center of mass concept, we came to the law of conservation of the linear momentum of system, that is the p equal to constant. Law of conservation of linear momentum of a system of particles. So the We followed here references by here Araskurmi, Ring Shams, Hibler, and also Google search engine, and also Beach Johnston we followed. With this, we can wind up the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.